Welcome back, everybody, to another deep dive.
Yeah.
Today we are going to be going way beyond like the sleek interfaces and apps that we're all used to seeing and using every day, and really try and get down to the nuts and bolts of operating system.
Oh, yeah.
You know,
The hidden world.
you use one every day.
Right.
Like every time you use your phone,
It's the invisible magic.
every time you use your computer.
Yeah.
Have you ever stopped to think about like what's really going on
Underneath.
under the hood
Most people don't.
to make all this stuff work?
No, and they don't realize how complex it is.
Yeah.
I mean, really, we're talking about managing everything from the CPU and how much processing power different programs get to memory to storage, and it all just seems to work
Right.
seamlessly.
It's just magic.
Right.
Like, I don't know how it works,
Right.
but thank goodness it does.
Yeah.
So for today's deep dive,
Yeah.
we're using an excerpt from a classic textbook called Operating Systems, 3 Easy Pieces. And we're going to be unpacking some of the core concepts that make this digital magic happen.
It's a great resource
Yeah.
for understanding the fundamentals, even if the title is a little bit tongue-in-cheek.
3 Easy Pieces.
Operating systems are anything but easy.
Yeah, definitely not 3 easy pieces.
Yeah.
All right, so let's start with like the big picture.
Okay.
If you had to just explain the essence of an operating system, like what would you say it's really all about?
I would say at its heart, an operating system is like this ultimate resource manager.
Okay.
So imagine a bustling city, you know.
Okay.
The operating system is like the city planner.
Okay.
It's making sure everything runs smoothly.
Uh,
It's allocating different resources,
Yeah.
like CPU time, how much processing power different programs get memory to different programs,
Like it.
managing traffic flow between different components.
Yeah.
And then also like enforcing the rules of the road to try and like
Okay.
prevent crashes and conflicts.
Oh, so it's like a traffic cop too, making sure that everybody's playing by the rules.
Exactly.
That's a great analogy.
Thanks.
I mean, it's mind-boggling to think about how much is happening behind the scenes. Like every time I open an app
Right.
or browse the web.
You just expect it to work.
Yeah, and it does.
Right.
It's amazing.
Yeah. And it's a testament to the brilliance of the people who work in this field,
Yeah.
I mean, the book actually points out that, a surprising number of Turing Award winners.
Oh, wow.
The Nobel Prize of Computing have made major contributions to operating systems.
Really? I had no idea.
Yeah.
It definitely speaks to like the importance and the intellectual depth of this field.
Absolutely. It's not just about writing code.
Right.
It's about solving fundamental challenges in computer science.
Yeah.
And one of those challenges, and concept I find particularly fascinating, is this idea of virtualization.
Okay, here's where it gets really cool.
Yeah.
Virtualization.
Virtualization.
It sounds like something out of a sci-fi movie.
Yeah.
What is the magic trick behind it?
Well, think about it. You might have multiple applications open on your computer right now.
Okay. Sure.
A web browser, a music player,
Uh-huh.
maybe even a game in virtualization is how the operating system makes it seem.
Okay.
Like each of those programs has its own dedicated CPU and memory.
So it's like creating a separate little world for each program to live in.
Exactly.
That's cool.
But here's the kicker. They're actually sharing those resources.
Um,
The OS is constantly switching between them, allocating CPU time slices and memory pages so quickly that it appears seamless to the user.
Wow. So it's like a master illusionist, creating this illusion of dedicated resources
Yeah.
while juggling everything behind the scenes.
Precisely. And the OS has these clever mechanisms like these base and bounds registers, which act as like these fences
Okay.
to control what each program can access in memory. It's all about creating a safe and controlled environment where multiple programs can run concurrently without interfering with each other.
That makes sense. So if virtualization is the illusion,
Yeah.
then memory management must be the stagehand making it all possible.
Memory management is absolutely critical for keeping this illusion going.
Right.
One of the techniques the OS uses is called segmentation.
Segmentation.
So imagine you're like organizing a play.
Okay.
You wouldn't just throw all the actors and props and costumes onto the stage at once, would you?
That would be chaos.
Exactly.
Yeah.
Similarly, segmentation is about breaking a program's memory into logical chunks,
Uh-huh.
kind of like dividing a play into, acts and scenes.
Okay.
So you have like the code segment where the program's instructions live.
Okay.
You have the heap for dynamic data,
Uh-huh.
and then you have the stack for like managing function calls.
So it's like creating order out of potential chaos,
Yeah.
but organizing the memory space really strategically.
Precisely, and this organization has some nice benefits. For example, segmentation helps prevent one program from accidentally overwriting another program's data,
Oh, that's good.
which could lead to crashes
Right.
or unpredictable behavior.
Makes sense.
Yeah.
But I'm guessing there are also some limitations to segmentation.
You're right. One of the challenges is that these segments can be of different sizes,
Okay.
which can lead to wasted space. It's like having a bookshelf with books of all different heights.
Right.
You end up with gaps and empty spaces
Yeah.
that could be used more efficiently.
Yeah, you got to get those bookshelves. You can adjust the heights of the different shelves.
Right, exactly.
So how do operating systems address that problem?
That's where paging comes in. It's a more refined approach to memory management.
Paging.
Yeah.
Okay.
And it helps to overcome some of the limitations of segmentation.
Got it. Paging, it sounds like we're flipping through a giant book of memory.
Yeah.
Is that the right mental image?
It's not far off. Imagine that both the program's virtual memory
Okay.
and the computer's physical memory are divided into these fixed-size chunks called pages. It's like having this massive organized chessboard
Uh-huh.
where each square represents a page.
Okay, so instead of these variable size segments, we have these like neat uniform pages.
Right.
How does that help with like that wasted space problem we were talking about?
Well, the beauty of paging is that it allows the OS to allocate only the pages a program actually needs at any given moment.
Okay.
Not all parts of a program are active at the same time. So inactive pages can be swapped out to secondary storage,
Okay.
like your hard drive,
Okay.
and brought back in only when they're needed.
So it's like having a giant library
Yeah.
where you can keep the most frequently used books on readily accessible shelves.
All right.
And then you can store like the rest in the archives until somebody requests them.
Exactly. And this ability to swap pages in and out is what allows us to run programs much larger than the available physical memory. You know, think about it. You can have multiple applications open, each with gigabytes of data, even if your computer only has a few gigabytes of RAM.
It's like magic.
Yeah, well, it's paging.
So paging is the reason we can multitask like so seamlessly on our computers and our phones.
It's one of the key enablers.
It's amazing how this like seemingly simple concept
Right.
has like revolutionized computing.
Yeah, it's pretty fundamental.
But I'm curious, like, how does the OS keep track of all these pages?
Right.
Like flitting between memory and storage.
Yeah.
It just seems like a logistical nightmare.
Yeah, it's a very complex task.
Yeah.
The OS maintains this special table
Okay.
called the page table,
Page table.
which acts like a map between the virtual addresses used by the program
Okay.
and the physical addresses where the pages are actually located.
So every time a program needs to access like a piece of data, the OS has to consult this page table
Right.
to find the corresponding physical address.
Yeah.
Doesn't that slow things down?
Yeah. It could, but the OS designers are always thinking up performance.
Okay.
So to speed up this address translation process,
Okay.
there's a special cache called the Translation Look-Aside Buffer,
Okay. Another acronym.
or TLB for short.
TLB. Okay. Break that down for me.
Think of the TLB like a cheat sheet for the OS.
Okay.
It stores the mappings for recently used pages,
Uh-huh.
so the OS doesn't have to go through the whole page table every time.
Okay.
It's like having a shortcut to the information you need most often.
So it's all about optimizing for efficiency.
Exactly.
Got it. Okay. But what happens if a program tries to access a page that's not currently in memory?
That's when we get what's called a page fault.
Page fault.
It's like hitting a detour on your way to a destination.
Okay.
You have to take this unexpected side trip to retrieve the missing page from secondary storage.
So the OS is constantly juggling all these requests,
Uh-huh.
swapping pages in and out, making sure everything runs smoothly.
It's a very dynamic process.
Even though it's this incredibly complex, like, ballet happening behind the scenes.
It is a beautiful dance.
It is, yeah.
Speaking of juggling,
Okay.
let's talk about scheduling, which is another crucial role of the operating system. Scheduling.
Okay.
Think of the CPU as this valuable resource
Okay.
that needs to be shared among all the running programs. The OS acts like a conductor,
Okay.
deciding which program gets to use the CPU when.
So it's like the time management expert, making
Yeah.
sure every program gets its fair share of CPU time.
Precisely. And there are different scheduling algorithms,
Right.
each with its own strength and weaknesses.
Mm-hmm.
One common algorithm is called round robin,
Round robin.
which is all about fairness.
Okay, tell me more about round robin.
Okay. Imagine you have like a group of people
Okay.
waiting to use a shared resource like a microphone.
Okay.
Round robin would give each person a fixed amount of time to speak
Uh-huh.
before passing the microphone to the next person in line.
Okay, so everybody gets a turn.
Everybody gets a turn.
That makes sense, but wouldn't that potentially slow things down if, like, some people have more to say than others?
You're right. That's one of the trade-offs with round robin.
Okay.
If a program has a long task to complete,
Uh-huh.
it might be interrupted multiple times
Yeah.
before it can finish.
It's like having to constantly stop and start your story
Yeah.
because somebody else wants to chime in.
Exactly.
Yeah, that's so frustrating.
Right.
Okay, so are there other algorithms that try to optimize more for, like, efficiency rather than just fairness?
Absolutely. Another algorithm called shortest job first
Shortest job first.
tries to prioritize the programs that are expected to finish their tasks the quickest.
Okay.
The idea is to get those shorter tasks out of the way quickly, which can improve the overall system performance.
It's like letting somebody with a quick question cut in line at the grocery store.
Yeah.
It gets them out of the way quickly and benefits everybody in the long run.
Exactly. But of course, there are downsides to this approach, too. If a long-running program keeps getting pushed back
Mhm.
because shorter tasks keep arriving,
Yeah.
it might never get a chance to finish.
Oh, no.
It's like being stuck at the back of a line
Uh-huh.
that never seems to move.
Oh, the worst.
Right.
So it seems like there's no, like, perfect scheduling algorithm.
Right.
It's all about balancing these different trade-offs
Exactly.
depending on the specific needs of the system.
Precisely. Real-world operating systems often use like a combination of sophisticated techniques
That's
to
right.
try and find the best balance between fairness, efficiency, and responsiveness.
Right.
It's a constant challenge for OS designers to find the sweet spot.
Wow. It's incredible how much complexity is involved in something as seemingly simple as deciding which program gets to use the CPU.
It's a surprisingly deep topic.
And we haven't even touched on concurrency yet, from what I understand. That's when multiple things are happening seemingly at the same time.
You've got
Right.
modern systems are all about concurrency,
Okay.
running multiple programs, or even multiple parts of the same program
Right.
simultaneously.
Yeah.
It's like a bustling city where everyone is going about their business at the same time.
So many things happening at once. It sounds chaotic.
It can be.
How does the OS manage to keep everything running smoothly when there's so much going on at once?
Well, that's where the concepts of processes and threads come in.
Process and threads.
Think of a process as this like self-contained unit of execution,
Okay.
like an individual apartment in that bustling city.
Okay.
Each process has its own memory space,
Okay.
its own resources,
Huh.
and it runs independently of other processes.
So processes are like these separate, isolated entities.
Yeah.
Okay, but what about threads?
Threads.
Where do they fit into the picture?
Threads are like the people
Oh, okay.
living within those apartments.
Yeah.
They share the same living space.
Uh-huh.
The process's memory and resources,
Okay.
but they can each perform different tasks concurrently. It's like having roommates who can cook dinner, clean the apartment, and watch TV all at the same time.
Oh, that's a good analogy. So threads provide a way to achieve concurrency within a single process,
Exactly.
allowing multiple tasks to happen in parallel.
Yeah.
That makes sense. But I imagine there are also challenges that come with having multiple threads accessing shared resources,
You're absolutely right.
right?
One of the biggest challenges is ensuring data integrity
Okay.
when multiple threads are trying to modify the same data at the same time.
Right, that makes sense.
You know, it's like having two chefs trying to use the same ingredients in your utensils simultaneously.
Right.
It could lead to a culinary disaster.
That's a great analogy.
So how does the OS prevent these data conflicts from happening?
Yeah, how does it prevent that?
It provides mechanisms like locks and condition variables,
Okay.
which act as safeguards to ensure that only one thread can access like a critical section of code or data at a time.
Uh-huh.
It's like having a rule that only one chef can be in the pantry at a time to prevent them from bumping into each other and messing things up.
So these locks and condition variables act like traffic signals, basically,
Yeah,
making sure that those threads don't collide and cause data corruption.
exactly.
It's amazing how the OS handles all this complexity
Yeah.
without us even realizing it.
It truly is a remarkable feat of engineering. Now, shifting gears a bit,
Okay.
let's talk about another essential function of operating systems,
Right?
managing how data is stored and retrieved.
Oh, yeah.
That's where file systems come in.
File systems,
Yeah.
they're like the librarians of our digital world,
Right.
keeping all our files and folders organized.
Keeping everything in order.
Yeah. I've always wondered how they work.
Well, think of a file system as this hierarchical structure.
Yeah.
It's like a giant filing cabinet
Okay.
with folders within folders.
Yeah.
Each file has its own unique identifier,
Okay.
kind of like a library card.
Sorry.
And the file system keeps track of where those files are located on the storage device.
Okay. That makes sense. But have you ever thought about how those files are actually represented on the physical disk?
It's actually quite interesting.
Yeah.
Files are typically divided into blocks of data,
Okay.
and those blocks are scattered across the disk.
Oh, wow.
The file system has to keep track of which blocks belong to which files,
Okay.
kind of like a giant jigsaw puzzle.
So it's not as simple as just storing a file in one contiguous chunk on the disk.
Not necessarily, as files are created, deleted, and modified. Free space on the disk can become fragmented,
Okay.
leading to those blocks being scattered all over the place.
So it's like trying to fit all your belongings into a suitcase after a long trip.
Yeah,
You end up with things just crammed in wherever they can fit.
exactly.
That sounds inefficient.
You're right. Fragmentation can lead to performance issues
Okay.
because the disk head has to jump around to access different parts of a file.
So it's having to work harder
Yeah, it's not as
to
efficient.
get to all the pieces.
Right. Some file systems employ techniques like defragmentation
Fragmentation.
to try and consolidate those scattered blocks
Okay.
and improve performance.
So it's like reorganizing your suitcase.
Yeah,
To make everything fit neatly and make it easier to find what you need.
exactly.
That makes sense.
And just like there are different ways to organize a suitcase,
Right.
there are different types of file systems, each with its own strengths and weaknesses.
Okay.
For example, some file systems are optimized for speed,
Uh-huh.
while others prioritize reliability or security.
So it's all about trade-offs again.
Always trade-offs.
Yeah, it makes you realize that there's a lot more thought that goes into file systems than just like storing and retrieving files.
Absolutely. And speaking of reliability,
Okay.
let's talk about data integrity,
Data integrity.
which is a crucial aspect of file system design.
Oh, yeah?
We've already touched on techniques like checksums,
Right.
but there are many other mechanisms in place to protect our data from corruption or loss.
Checksums, they're like those digital fingerprints
Yeah.
that can verify if a file has been tampered with.
Exactly. Checksums are widely used to detect errors that can occur during storage or transmission.
Uh-huh.
But what if the problem isn't just a random error, but like a misdirected write?
Misdirected right. What does that mean?
Imagine you're writing a letter,
Okay.
and instead of putting it in the correct mailbox,
Uh-huh.
you accidentally put it in the wrong one.
Okay.
That's kind of what a misdirected write is.
Ah.
Data gets written to the wrong location on the disk.
So it's like a postal service error in our computer.
Yeah, kind of.
That sounds dangerous.
It can be. Fortunately, modern file systems have ways to prevent these mishaps.
Okay, good.
They use sophisticated techniques like journaling,
Journaling.
which is like keeping a detailed log of all the changes being made to the file system.
Okay.
If a crash occurs in the middle of a write operation, the journal can be used to recover and restore the file system to a consistent state.
So it's like having a backup plan for when things go wrong.
Precisely.
That's a good thing.
Yeah, and in addition to journaling, some file systems use techniques like copy on write,
Copy on right.
where changes are made to a copy of the data first,
Mm-hmm.
and only after the write is complete is the original data updated.
Okay.
This helps to prevent data corruption in case of a system crash or power failure.
Wow, it's incredible how much effort goes into ensuring that our data is safe and sound.
Yeah, it's a top priority for file system designers.
Yeah, makes sense. It really makes you appreciate the complexity and ingenuity behind operating systems.
It's a testament to the brilliant minds who have dedicated themselves to building these intricate systems that power our digital world.
Yeah.
And the journey of innovation continues
Yeah.
as new technologies emerge and new challenges arise.
I have to say, this has been an eye-opening deep dive into the world of operating systems.
Yeah, me too.
It's
Yeah.
amazing how much we rely on these complex systems every day without even realizing it.
It's true. Operating systems are like the unsung heroes of computing. working tirelessly behind the scenes
Yeah.
to make our digital lives possible.
Thank you so much for guiding us through this fascinating world.
Oh, my pleasure.
It's been a pleasure to learn from you.
It's been fun talking with you too.
And to our listeners out there, I hope you found this deep dive as insightful and engaging as we did.
Yeah, and remember, the next time you interact with your computer, take a moment to appreciate the silent symphony of the operating system,
Oh, yeah.
orchestrating all the digital magic beneath the surface.
Great advice. Thanks for joining us on this deep dive, and until next time, keep exploring.
Keep learning.
It's like having this extra layer of protection to make sure that our data is safe,
Exactly.
even when things go wrong.
Yeah. It's fascinating to think about all these different layers of complexity
Yeah.
that go into making our computers work reliably.
Right, because we just take it for granted.
We do. We just expect it to work.
We hit save.
Right.
We expect our data to be there.
And it almost always is, which is a testament to the hard work of a lot of very smart people.
It is. It really is.
Yeah.
And we've only just scratched the surface of operating systems in this deep dive.
Yeah.
There's so much more to explore.
There are entire books written on just like one aspect of operating systems.
Really?
Yeah.
Wow. I have to say, this has been an incredibly eye-opening journey
Yeah, me too.
into the hidden world of operating
So
systems.
there's like a whole universe underneath our fingertips.
It is, yeah. And it's amazing to think that all of this complexity is happening every time we use our computers or our phones.
Yeah, it really makes you appreciate the power of abstraction.
Abstraction.
Yeah, you know how operating systems hide all this complexity
Right.
behind these simple
Because
interfaces?
they can just focus on what we want to do.
Exactly, without having to worry about all the nuts and bolts.
It's a beautiful thing.
It's one of the things that makes computing so accessible to everyone.
Yeah, that's a great point.
You don't need to be a computer scientist to use a computer,
Right.
but it's fascinating to peek under the hood
It is.
and see how it all works.
I totally agree. Well, thank you so much for being our guide on this amazing deep dive.
My pleasure. It's been a lot of fun talking about operating systems with you.
Yeah, it's been really fun for me too. And to all our listeners out there, thank you so much for joining us on this journey into the heart of operating systems.
Yeah, we hope you learned something new.
And that you'll never look at your computer the same way again.
Right.
Until next time, keep exploring and keep learning.
And keep diving deep.